So thank you, Tricia, and thank you, everyone, for joining us here on this cold Monday night in June. The goal of tonight's talk is to provide a practical overview of regularization, which is a key statistical concept, and to examine closely one recent technique that allows us to solve very large regularized problems. So the agenda for tonight, first half is mostly a review for those of you less familiar with the topic. The core of the talk is in the second half, and in particular, I'll go into detail on the math, on some of the math of coordinate descent algorithms. Having a good understanding of how these methods work is useful because it allows you to more effectively set or adjust the control parameters of any software that you may be using that implements these algorithms. And lastly, an example from text mining where a large number of predictors easily arise. So what is regularization? So regularization refers essentially to methods intended to control variance, which is the variability in the estimates of the parameters of our models. There are different ways of achieving regularization, such as explicitly via constraints on model complexity, and that's the kind of regularization that we're going to be talking about tonight. Implicitly through incremental model building. Those of you familiar with the boosting algorithm, boosting does an implicit form of regularization that way. And we can also do regularization via robust loss functions. So in terms of timeline, here are roughly 15 years worth of R&D in this domain. The list is not meant to be exhaustive, but representative. And starting at the top, Breimann's garrote was probably one of the earliest attempts at controlling the variance in the estimates in an ordinary linear regression. And so, but Breimann's garrote was a post-processing algorithm. So it will run a traditional ordinary linear regression and then post-process those coefficient estimates. Tibshirani's lasso built on the garrote ideas, but it doesn't make explicit use of the ordinary linear regression coefficient estimates. Then the Lars algorithm by Efron provided a very, very efficient way of computing the lasso coefficients for a particular error measure, the square error. The path-seeker algorithm of Friedman used a gradient descent approach, which allows computing regularized coefficients for other error measures beyond square error loss. Then ElasticNet is one example of what we will describe in tonight as bridge regression. Then the coordinate descent algorithm described in this reference, among others, so coordinate descent is described in different places, supersede the path seeker as the fastest algorithm for computing the lasso coefficients. And the GPS algorithm extended the gradient approach to non-convex penalties, which we'll see an example of that, which is appropriate for in problems where more regularization is required. And then a couple of more recent references. The PMD algorithm, it's for doing matrix decomposition with a sparse singular vector. So that's a very interesting work too. And then the Bayesian lasso work is exploring how to compute confidence interval around the lasso coefficient estimates. So the original lasso paper did have some suggestions for computing standard errors for the coefficient estimates, but several difficulties were left unresolved. Like for instance, if the coefficient ends up being 0, the corresponding standard error was 0. So it's like you had certainty that the coefficient was 0, and that's not the case. But tonight we're going to be talking mostly about the coordinate descent algorithm. So next, a brief section on predictive learning, primarily to set up notation and provide some motivation for the regularization problem. And so typical notation, the predictive learning problem, we're given some training data, pairs X and Y. I'm using big N or capital uppercase N for the size of the training data, and little n for the dimension of the input vector X. This data is assumed to come from some unknown probability density function. And then we want to use this data to build a model that offers an adequate and interpretable description of the connection between the input and the output. And adequacy is often defined in terms, adequacy or goodness is often defined in terms of prediction accuracy, but parsimony is often an important criteria as well. So it's the idea that simpler is better, even if it's just for the sake of insight. Then once we have the data, we want to specify as well a model as core criterion and a search strategy. So the model is the functional form that we're seeking from the data. In the discussion tonight, the functional form is going to be linear. But because the predictor, the x's, can be the original measure variables or functions derived from them, the framework is quite general. The score criterion consists of two parts. The loss, or such as the square error loss for regression problems, or the binomial likelihood for classification problems, and what statisticians call risk, which is the expected value of the loss. And then finally, we need a method to find the value of A that minimizes the risk. And coordinate descent is going to be one such method. In practice, however, the probability density function of the data is not really known. And so we minimize what is called empirical risk instead. And so the notation that I'm going to be using, so A for the coefficient vector or the parameters of the model, L for the loss, R hat for empirical risk, and so on. So consider next, by way of motivation, the problem of fitting linear classifier to these two-class data. And it's using either one variable, two variables, or three variables in this case. So if we look at the projections, so we see that a size 1 model, say the projection to x1 or the projection to x2, might do poorly. But a size 2 model might do much better. Even as a size 3 model might do great, but if the n isn't large, there will be a lot of uncertainty in the estimate of the slope of the hyperplane that defines the classifier. And so the model size dilemma is this, right? If the model or the number of variables is too small, then the approximation is too crude, and we have what we call bias. If, on the other end, the model is too large, then we are exposed, we have more chances of overfitting, and we have what is called variance. And regularization, as I was saying earlier, is intended primarily to control the variance. So let's now talk about regularization in a linear regression context. So the functional form of a linear model is just that. What did I do with my? Yeah, let's see here. And so that's, we got the mic working again? No, it's not. OK, thanks. So this is a functional form of a linear model, very straightforward. And this is the corresponding expression for the empirical risk for a linear model. Now, if the loss is a square error loss, then this solution can be obtained by direct matrix algebra, right? So this is what is called the pseudo-inverse. And it always exists. However, there are at least two problems with this ordinary linear regression solution that makes it often unsatisfactory. One is prediction accuracy, so this issue of high variance in the coefficient estimate, and the other one is interpretation, right? This desire that we have for identifying a smaller subset of predictors that have the biggest, that exhibits the stronger effects in that connection between the inputs and the outputs. And two common approaches at trying to estimate over the OLR solutions are subset selection and regularized regression. And regularized regression is often preferred because it's a continuous process. So regularization consists of augmenting the expression that we have for the empirical risk with this complexity penalty. This is a non-negative function, and as the size and number of coefficients grow, the value of the penalty increases. The complexity threshold T mediates the bias and variance trade-off. So if T is close to 0, we have maximum regularization, simplest model, or equivalently maximum bias, but smallest variance. At the other end, if the threshold is very large, then the complexity penalty plays no role, and we get back the original ordinary linear regression estimates. We do not increase the bias of the model, but we have maximum variance. I'll get to that thing. Notice also that P doesn't depend on X. And so we said that P is independent of the particular random sample. And that's where the variance is coming from, right? The variance comes from the data. But P doesn't depend on the data. So we say that P is deterministic and thus provides this stabilizing influence. And in terms of guidelines for choosing P, one driving or one guiding principle is that so A star is the optimal solution, right? If our solution is close to the optimal solution, the solution that we are obtaining using the data that we have, we expect that the sparsity of our solution is similar to the sparsity of the optimal solution. And so we want penalties as a guiding principle. We want penalties that can generate solutions of various degrees of sparsity. And I'll come back to this point later. Now, the constraint formulation has an equivalent penalized form where we are adding the penalty function to the criterion being minimized. And here, the complexity parameter lambda plays an equivalent role or an analogous role to the complexity threshold T. And so, like when lambda is close to infinity, the penalty is maximum. When lambda is 0, the penalty plays no role. And so we say that the penalty penalized for the increased variance associated with more complex models. So we know the more complex and flexible the model is, the more chances of overfitting. And so that's what this penalty is trying to do. notice also that for different values of lambda, we obtain different solutions. And so as I mentioned earlier, if lambda is equal to 0, there's no regularization, and we have the ordinary linear regression coefficient estimates. And if lambda is equal to infinity, we have maximum regularization, and only the intercept term, A0, which is often outside of the penalty, is the only model that we obtain. All the coefficients are 0, and we only have the offset term. And so this sequence of coefficient values, one for each predictor, as we vary lambda from infinity down to 0, are known as coefficient path. And so here's an example of coefficient path. In this problem, there are 8 predictors. And again, we start on this extreme, on the left-hand side, where lambda is infinity. And then as we relax the value of lambda down towards 0, more coefficients become non-zero. And the optimal value of lambda lies somewhere along that path. Notice also that these coefficient paths are piecewise linear. This is not always the case, but it's the case for certain combination of the penalty and the loss function. And this is a property that is exploited by some of the algorithms, like the Lars algorithm. Now, given a particular loss, like a square error loss, and a particular penalty, and I'll be showing examples of penalties later on, then the problem of finding the optimal value of lambda, where that red line was in the previous image, is a typical model selection problem, right? So we finding the value of lambda that minimizes our augmented risk. It's a typical model selection problem that is often dealt with using cross-validation. And so using a predefined grid between alpha mean and alpha max, so instead of 0 and infinity, we can narrow that range a little bit more. So the challenge, of course, is how to rapidly produce this path without repeatedly optimizing. And that's where these direct path-seeking algorithms that I'm going to be talking about tonight comes into place. So you can solve any of this with a standard optimizer, but that will be too slow. And so some of the examples of direct path-seeking that I mentioned in the timeline, one of the earliest ones is the forward stage-wise algorithm, then the Lars algorithm by Efron, then path-seeker, and more recently, the coordinate descent approach. Any questions so far? So let's look at a couple of examples of penalties and their properties. So one of the best, most well-known penalties is what is called the Rich penalty. And compared to the ordinary linear regression coefficient estimates, the Rich penalty shrinks the coefficient towards 0. So by looking at the definition of the penalty, as the magnitude of the coefficients grow, the penalty grows. So the effect of having the Rich penalty in the risk minimization procedure is to pull them back towards 0. However, Rich tends to produce what I've been calling dense solutions, that is coefficient vectors where the majority of the coefficients are non-zero. And as such, Rich is best for problems where there is a large number of small effects, and there aren't that many correlated variables. right? Because in the extreme case that if we had k identical predictors, what Rich is going to do, it's assign to each of them one case of the value of the coefficient if only one of the variables was present. On the other hand, the lasso penalty is capable of generating sparse solutions, namely coefficient vectors where many of the entries remain 0. And as such, the lasso penalty is best suited for problems with a small to a moderate number of medium-sized effects, and is somewhat indifferent to very correlated predictors. The lasso penalty will try to pick one representative of the set and ignore the rest up to a limit. So let me go back to this notion of sparsity and density, and let's consider this more formal definition of sparsity. So if the predictors have been standardized, so sparsity is just the number of predictors that are 0 or close to 0. And so so we expect that, so A of lambda is our best estimate of the coefficient vector. So we expect that if A of lambda is close to the optimal solution, we expect the sparsity of the solution that we propose to be close to the sparsity of the optimal solution, as we were saying earlier. And that because of this expectation, in the absence of additional information, we want penalties that are capable of generating various degrees of sparsity. Of course, the sparsity, since A star is not known, the sparsity of A star is not known. And so what we want is really not just a penalty, but a family of penalties, where this parameter alpha indexes the degree of sparsity of a particular solution. And so now we have two metaparameters. We have the lambda that is controlling shrinkage, the pools towards 0, and we have alpha. And so now we have the model selection problem we restated in this way. So, and this approach, it's known as bridge regression, and was first proposed by Frank and Friedman in the early 90s. And one example of a bridge penalty is known as elastic net. And so we see the alpha here. So we see that the elastic net, when alpha is equal to 0, we get back the ridge penalty. And when alpha is equal to 1, we get back the lasso penalty. And so we say that the elastic net bridges between the lasso and the ridge regression, because in advance, we don't know which is the right penalty for a problem. So what we want is a family of penalties so that we can explore both degrees of sparseness. And as I mentioned earlier, we need to do model selection to estimate both alpha and lambda, which it sounds like a lot of computation that needs to be done, ergo the need for very, very fast algorithms. Another example of a bridge penalty comes from the power family. And notice that this one straddles a wider region of the sparsity continuum. And so when alpha is equal to 0, then the penalty is just as if we were counting the number of parameters that are non-zero. And that's analogous to doing all subsets regression, and that's the sparsest solution that we can generate. If alpha is equal to 1, we get the lasso. If alpha is equal to 2, we get the ridge regression. But notice that for alpha less than 1, the penalty is non-convex, right? So this is alpha equal 1, this is alpha greater than 1, and all these penalties are obtained when alpha is less than 1. And so we need these pathfinding algorithms via generalized gradient descent to handle this case. So this is the GPS algorithm that I was mentioning in the timeline is an example of that. Yeah.
Is there a use of training set, test set to search over those lambda and alpha parameters, or?
Yes. So I mentioned, so model selection, if we're doing it, if you have enough data to have training and test set, then you don't use cross-validation. Otherwise, you use cross-validation. But it's a typical model selection approach. It's the same way that you're trying to decide the size of your neural net, maybe even the number of support vectors. You're doing model selection here to find the base value of alpha and lambda.
And is it looking at just the results on the test set?
Yeah.
Or is it looking at any kind of gap between training and test to see?
No. Primarily, I mean, you could come up with some fancy scheme like that, but primarily, yeah, you're fitting the model. You are going to generate a grid on alpha, a grid on lambda. You solve, you find the coefficient vector that solve for that, and you test it on the test data, or if you're doing cross-validation. So yeah, standard model selection approaches. Yes. And so that takes us to these pathfinding algorithms via gradient descent. So let me provide first an overview of direct pathfinding methods, and then we'll jump into the coordinate descent. So one way of understanding direct pathfinding is to imagine if we can come up with this two-step process. We start by specifying the starting point and the ending point of the path. So I'm referring to the coefficient path that we had a picture as we go from total regularization or maximum regularization to no regularization, right? And so so we know the starting point. The starting point is total regularization. All the coefficients are 0 except the intercept term. To no regularization, where we get back the ordinary linear regression coefficient path. And so we have the starting point, we have the ending point, and we need a prescription for given a position along this path, say A sub nu, how do we get to the next point along that path? And so we need a direction vector and a step size along that direction. And different algorithms differ for the specification of D and delta. So for instance, the Lars algorithm, at every step, it finds the subset of variables that is most correlated with the residuals at that point, and then it moves in a direction that is called equiangular between the subset of variables. And so different methods differ for the specification of D and delta, but they all share a risk monotonicity property. Namely, every subsequent point in the path has a lower empirical risk on the training data. And so you can think of D as a gradient, as a descent direction, or D projects positively on the negative gradient. So from this perspective, these methods can be thought of as numerical risk minimization procedures. But the emphasis here is on path traversal, namely recipes for D and delta that will mimic or generate paths that are very close to the path that we would have obtained if we were solving the problem with standard optimizers over and over and over again as we vary the values of alpha and lambda. graphically, the pathfinding algorithm can be viewed like this. So these paths are in coefficient space, right? And so let's say that at the beginning, we just have an estimate for the intercept for A0, and then we start finding the sequence of coefficient vectors. And a standard loop like this, where at the beginning, all the coefficients are equal to 0, and then we update the coefficient vector one step at a time. This algorithm usually proceeds until, say, some minimum of empirical risk on the test data, for example. And so, for instance, the path seeker algorithm that I mentioned earlier uses a D vector related to the gradient vector. So I was saying, Lars doesn't use gradients at all. The Lars algorithm has its own prescription for D and V. Path seeker uses a D vector defined in terms of the gradient vector. So notice that, so implementing this algorithm would be straightforward. And you can think of a coordinate descent algorithm that goes something like this. So find the predictor variable that has the steepest descent direction, and then update that coefficient by an infinitesimal amount. But those procedures will be too slow for the kind of problems that we're trying to solve here. And this need for computational efficiency take us to the coordinate-wise descent algorithms. The idea is very simple. So instead of doing infinitesimal step along one coordinate, we're going to loop through all the coordinates, through all the variables, and we do full minimization along that variable. At the April meeting of the ACA, at the local chapter of the ACA, Professor Tipshirani talked on this same topic. And the analogy that he used was, so suppose you are skiing in Tahoe, you're trying to go downhill, and so what you're going to do is you're going to go east, then west, then north, then south, and then you keep looping around like that. If the variables were not correlated, one minimization would be enough along each variable. But because there are correlations, we have to loop, repeat this process multiple times. So at least compared to what I said earlier, we are doing a minimization all the way as opposed to the infinitesimal step. Yeah.
As opposed to many local steps.
Kind of. And of course, but as a follow-up to that answer, this is particularly efficient when the minimization along one coordinate can be done very, very quickly.
Like in one step?
We'll see that the operations that are required to do that minimization is like dot products or something very, very simple. And we'll see in the next slide that, for instance, when the loss is a square error loss and the penalty is elastic neck, it happens to be that way. Yes?
Can you do a conjugate gradient type of descent so you have a finite number of steps to reach the mean?
You could. The claim is that this is way, way faster than that.
I see.
Yeah. And I should say that coordinate-wise descent is not a general optimization method. It doesn't work for many, many convex problems. But it happens to work for functions that look like this. And this looks a lot like our expression for augmented risk. So this is the, so G has to be differentiable and convex. And so many of the, depending on the loss, if we're using a square error loss, the expression that we have for risk happens to have this form. And the penalty has to be additive, and each of the components here, it's also convex. So if we're using elastic neck, it falls into this form. So I guess we got lucky that the form of the regularized problems that we're trying to solve for various combinations of loss and penalties happens to be of this nature. And so it's a fortunate thing. Yeah. So let's look at the special case of the loss being least squares and the penalty being the elastic net, right? So we were calling the combined expression R tilde, and the first part is just the risk, right? When the loss is a square error loss. And the second part is just elastic net penalty, right? And so if we're going to apply coordinate-wise descent, what we are saying is, suppose that we have the estimates for A0, and we have estimates for all the other variables, and we want to optimize with respect to a single variable, right? Let's say A sub j. So we need the gradient of this expression with respect to A sub j. And let's try to work through that gradient calculation, because with a square error loss, it's really straightforward. So, OK, so this is what we are after. And so because of this absolute value here, we have to do this by steps, so the positive side and the negative side. So let's look at the positive side. And so so we are taking the derivative of this expression with respect to A sub j. So so what comes out of here is a xi sub j. And the other thing so this is just an expansion of this dot product, right? X times A. And this A sub j came out of here because a typical pre-processing operation that is done is to do standardization. So you center the x's and you make the variance equal to 1. And so when we have this xi sub j here times this xi sub j in this sum, that's 1. The dot product of xj times xj is going to be 1 because they have been standardized. And so the A sub j came out of this sum. So that's what happened there. And then on this side, it's simpler. And so this is just A sub j times lambda times 1 minus alpha. And then we are assuming that we are on the positive side. So the derivative of this is just 1. So we get lambda times alpha. So, so that would be the expression for the gradient. And there's a very similar expression for the negative side. And then if we equal the gradient to 0 and we solve for A sub j, that's what we're trying to find, right? The minimization along the coordinate x sub j. So notice, like in the positive side, if we make this equal to 0, we have A sub j times 1 minus this, and that's going to go to the other side to divide, and that's what we have here. And then this expression minus this. And so this S here is what is called the soft thresholding operator, which is simply allows us to put the negative side and the positive side in the same expression. But the soft thresholding operator, when this argument is greater than 0, the soft thresholding operator returns this minus this, which is what I was walking us through. So this is the minimum along that coordinate. And this expression, so let's look at this expression, and also here I introduce the notation y tilde, which is, so y tilde instead of y hat is the current estimate of the model, but it lags the x sub j piece. So that's what this at the top means, is the current y hat without the x sub j component. So it's just this. I'm replacing this sum here by this y tilde. So let's look at that expression inside the soft thresholding operator, and why computing this can be done very, very efficiently. So we can add and subtract inside here. We can add and subtract xij times aj. So we're just trying to complete the estimate of y sub I, right? And so when we complete it, this r is what we call the residuals. So this r sub I is just y sub I minus y hat sub I. So we just added and deleted the term that was missing here. And one term got absorbed into this residual, and the other term is here. That makes sense? And again, because of standardization, when we do this xi times xij over here, xij, that's 1, and so the aj comes out. And so what remains inside the sum is just xij times the residual at that point. So a little bit more manipulation. So again, let's substitute the definition of the residual again. So this sum is just xij times y sub I minus y hat sub I. So this is the current prediction of the model, right? And so the first part, xij times y sub I, this is the dot product of x sub j and y, right? So these two parts is this dot product. And then inside here, the y hat, or the y sub I hat, I'm just expanding it, is the dot product of the current coefficient times the corresponding predictor, but only for those who are non-zero, right? And so this can be expressed as the dot product between x sub j and x sub k, this sum here, this double sum here. And so notice what happened at the beginning of the minimization. We can pre-compute all these dot products, so the dot products of every input variable and the response, and we store them. And we can also pre-compute the first time that a variable x sub j enters the model, namely the corresponding coefficient becomes non-zero. We compute and store all the dot product of that variable and all the other variables. And then if one coefficient changes, updating the gradient, this is fixed, so it's just multiplying these values that have been pre-computed by the coefficient that have changed. So that's, in a nutshell, why this algorithm is just amazingly fast, because it's just dot products. And dot products that can be recomputed. Some are pre-computed, and some are just computed when you need them. But this gives us the value of the coefficient along that coordinate. The procedure typically stops after a cycle where no new variable enters the model. And so just a couple of additional details. And so originally I was talking about lambda equal to infinity and lambda equal to 0, but then I say that can be further constrained so that we have a finite number of lambdas to explore. And so instead of lambda equal to infinity, we say lambda max is the smallest lambda that keeps the coefficient, all the coefficients equal to 0. And by the definition of the soft thresholding operator that we had a couple of slides ago, we can see that, or it's easy to see that the coefficients will remain 0 if this is true. And so we simply solve here for lambda max equal, so this alpha comes here to divide. And so, so again, what I'm trying to do is to arrive at a finite sequence of lambdas to explore. And so instead of lambda infinity, we can find this lambda max. And then typically, lambda mean is set to some fraction of lambda max, say 1,000 or 100th of lambda max. And then a sequence of lambdas is generated in this interval. And so some software by default will put 100 values in that interval. And so those are the 100 values of lambdas that we have to cross-validate.
Is it like an equal range or exponentially increasing?
It's a good question. Like some of the implementations that I've seen, like the GLNet package in R, which I'll demo shortly, it puts more. It has 100 lambdas in the log scale, so it puts more lambdas in the smaller region.
Right.
Yeah, but the point is that we can generate a fixed, not too large number of lambdas to explore. The alpha sequence, so remember, we also have the other metaparameter, the one that controls sparsity. And so the alpha sequence is usually smaller in the 0 to 1 range, like 0, 0.2, 0.4, 0.6, 0.8. Because remember, lambda equal to 1 give us dense solutions. Sorry, alpha equal to 1, depending on the elastic net, give us dense solutions. Alpha equal to 0 give us sparse solutions. So we want to explore all those degrees of sparseness. And additional optimization that is added to the algorithm is this notion of the active set. So at every iteration, the set of variables that are non-zero. And then, so it stays on that active set until none of the variable changes. And if no new variable, then it does one extra pass. And if no new variable is added to the model, then it stops. So that's the essence of coordinate descent. And so let's look at the example. Let's try to do it. Is that font readable from the back? No? So let's, all right. How about that? Oops. What happened to my mouse? Is that readable on the back? Okay. So let's. So I have here some R code. Let me start. Are there?
Your left margin is slightly cut off.
Okay. My left margin. Let's see if that's. I don't know how to do it. Thank you.
Yeah.
Okay. And so we'll just split this window and put the R code over here. And so one implementation of coordinate descent is in R under this library called GLNet. And so let me load that. Recently upgraded my version of R, so hopefully I'm not running into trouble, because that should have not taken this long. Okay, and so I want to load this data. So just reading the X matrix and the Y vector. And so let me pull them aside. So this is roughly 11,000 documents by almost 800,000 predictor variables. Right? And it's a very sparse metrics, right? Also, I should have said, if we go back to the algorithm, since it's mostly dot products, it naturally takes advantage of, or can take advantage of sparseness, because as you are doing the dot product, if one of the entries is not there, you just don't use it. So see, this is 5% of the data is present, so it's a very, very sparse matrix. And notice, like if I do, so what is this? Divided 1024 times 1024, 1024. Did I do that correctly? Oh, yes. So if we have, say, 8 bytes, so I will need 60 gigs to store these metrics if it weren't in a sparse form. And I don't have 60 gigs in this laptop. I only have 8. So it's taking advantage of the sparse matrix representation in R. Summary of Y, so it's a pretty much evenly split in terms of class 1 and class 2. And so we are trying, again, to fit a regularized logistic regression to this data. And this should take about a minute. So while this is running, let me show you other tools available in R to build that matrix. So depending on the size of the collection, like you can build the say the TF-IDF matrix in Hadoop, and then you just import it into R. Again, because it's a very, very sparse matrix, the traditional limitations of memory issues of R don't play a role here. If the collection is not too big, there is this library in R called TM for text mining. And so let me show you. So yeah, it starts roughly here, where I'm specifying so the first thing is to create a corpus. No, the first part is to create a corpus source, and so I have a configuration parameter that it's pointing to the path where the files are, and I'm reading. So in this inside this directory, I have 2 subdirectories, one called Y0 for class 0 and one called Y1 for class 1. And all the files begin with an ID followed by a number, all the text files in that collection. And then, so after we have a pointer to that directory, so what this will do is just grab the list of files. And then we call the corpus function from the TM package, and that reads all those files. And then if I move over here, then we do the traditional text mining steps. And so there is a TM map function that applies a function to every element in the corpus. So we do remove punctuation, we do remove numbers, we do remove f-top words. And if we're doing a stemming, and so we do a TM map of a stemmer. And at that point in time, we got our, at this point in time, we can call document term matrix, which will give us, as a result, the sparse matrix that we're going to use to feed into the regularized regression. So let's see if this already finished. Yes. And so, so it took, I guess it took 2 minutes to do this. I don't know why I was expecting it to take 1 minute. And so if we look at what did we get back in this object called fit news, so if we look at some of the attributes, and so for instance, the lambdas, let's look at the length of lambda. So it's 100. So what I was saying earlier, 100 different values of lambda get generated between lambda max and lambda min. And we get the betas, which are the coefficients. But so how many coefficients did we get? And so if we look at this, the coefficients is we have 100 values of lambda. And for each value of lambda, we get 777,000 coefficient values. Most of them, we hope, are equal to 0. But that's what we get there. If we pick a particular value of lambda, so we can retrieve the corresponding coefficients. So let me do this. And then, so again, this should be a vector of length 777,000. That's the number of predictors in our data set. And how many of them are non-zero? Only 766. And so that's what we are expecting from the regularized regression problem. Now, to do the model selection, we really need to do the cross-validation. And so there's a different call called CV-GLM-net. So we just did it for one fold. So if we were going to do cross-validation, it's going to take 10 times. So it took 2 minutes for one fold. If we were to do 10 times, it will take 20 minutes. So I won't make you wait for that. But I want to show you what I think I had it in the slides. So let me go back to the slides. So yeah. So in the call for CV-GLM-net, so this is so again this one. That's what I was surprised. This one took 10 times 60, which is what I was expecting on the first run. So just 10 minutes. I don't know what's different except that I upgraded in the last week my version of R. And when we do CV-GLM-net, so when we do cross-validation, we get an extra element in the result, this lambda 1SC. And so like in the case of decision tree, so that's the minimum plus 1 standard error. So that's the lambda where the minimum error was found plus 1 standard error. And so that's the lambda that we use to select the coefficient. After I did that, we got back 4,800 non-zero coefficients. So again, 4,800 out of 770,000 coefficients. And at that point, we can use that model to do a prediction. And in this case, it's pretty good. And so so that's the story that I wanted to tell you tonight. Bridge regression allows for both sparsity and shrinkage control. We now have this very fast algorithm for generalized linear models for a variety of error functions and penalties. So we can do linear regression, we can do logistic regression, we can do multinomial regression. And there is a version of the algorithm also available for non-convex penalties. So the non-convex penalties where we will do even more aggressive regularization will come into, for instance, some of these generic data sets where here in this case, yes, there are many columns, but we had several thousand rows in some of the generic problems. They have thousands and thousands of columns and just a couple of hundred rows. And so more aggressive penalty functions, non-convex penalty functions are needed. And the speed of the methods allow us to handle very large problems. And they are ideally suited for sparse data. That's all. Any questions? Yeah.
In a lot of cases, like when you're doing simple clever filtering kinds of things, and you have binary data, do these techniques apply there, or?
So sometimes, actually, the answer is yes, because I'm thinking. Yeah, sorry. So the question is whether these techniques can be used for collaborative filtering problems. And there are different ways of approaching the collaborative filtering problem, but one is do the singular value decomposition of the matrix, right? And so one of the references that I mentioned at the beginning, the PMD algorithm is doing matrix factorization, penalized matrix factorization, so that when you get back the singular vectors, they are sparse singular vectors. And so the answer is totally. Yeah. Yeah.
How well does this regularization work in stochastic setting when you have a very huge data set and you go through it on the ones?
My first reaction is I don't know. So we saw what we were doing, but namely I mean in a sense. So if I understand what you're saying is so we're doing the coordinate-wise descent, like okay, we got a current version of the data. And we do the minimization along this coordinate. But when we're going to do the next step, the data has changed.
Well, if you are going one example at a time as opposed to looking at the whole data set, right?
I mean, I don't know, but it sounds interesting. So remember, we're just doing dot products. Maybe the dot products are true 90% of the time, like a few minutes later or a few days later, 10% of the data has changed, right? That's a typical like real time. But if most of the dot product it's valid, maybe it works. I don't know. Yeah.
Can this be compared with SVM using sequential minimal optimization? Or can those handle like million parameter data sets?
I don't know. Sorry. But yeah, SVM in its traditional form, it's a regularized regression problem. It has a particular loss function, the hinge loss, and it can be recasted as a regularized regression. What is the penalty for SVMs? So there's a connection. I don't know if remember the coordinate-wise algorithm is not a general convex optimization paradigm. So it depends on the particular loss and the particular penalty. So I don't know. Yeah.
Is this algorithm fast enough for a learn, like a real-time learning? I mean, if your data set is constantly changing.
So that is related to the question of this gentleman over here. I was hypothesizing. So the essence of the algorithm is just dot products, right? And now, if you have a dot product of hundreds of thousands of rows and say 90% of that dot product remains valid over the next week or over the next few days, maybe. Yeah. That's a guess.
So basically, regression is a linear method. Like a decision tree can capture some interactions in one subtree versus another subtree. Because in your text mining, you might have mostly 0, 1 values. But in other problems, you might have more continuous values. So if variable A has a continuous range and interacts with a continuous range in variable B and variable C, is this going to capture any of the interactions, or basically have to do with the binning?
So
it's basically a linear method still.
Yes and no. Remember at the beginning when I said, okay, for tonight the functional form is linear, but the predictors could be the original measure variables or functions derived from them. And so the framework is quite general in that sense. In fact, the most advanced version of ensemble methods today use this as a post-processor. In other words, replace every X by a decision tree.
Okay.
And you have 100,000 decision trees.
That's just a linear layer on top of the thing.
But that is the general framework. If you look at the output layer of a neural net, the output layer of a neural net, it's linear on the hidden layer. The hidden layer is nonlinear. If you look at many kernel methods, it's a linear expansion on nonlinear basis functions. And so the method, it's quite general from that perspective. Yeah. Yes, sir.
Where can we get a copy of these slides?
Tricia will make them available on the.
And if you have corresponding R code that you were showing, that could be of interest too.
I had a related question. I never used R, but based on the program I see there, it looks like you have a lot of built-in functions in R to solve this text mining problem.
R rocks, man. I'm a big R guy. Yeah, and invite you to discover R.
I probably will after seeing this. I thought
Good.
it's worth investing my time to pick it up. So.
Yeah, and by the way, you don't have to pay for the software that I was demoing today. And so you are solving a problem with 1 million predictors in 1 minute, and it didn't cost you a penny. So, yeah.
Any open research problems in this region?
Certainly. So again, one that I mentioned on the this issue of computing the confidence interval around the estimates. Like, so we're getting a coefficient vector where some of the coefficients are 0 and some are non-zero. It'd be nice if we could have, for the ones that are 0, some notion of standard errors around it. So that reference that I have there, I know it's a PhD that it's being defended this summer. So I'm looking forward to that. I don't know whether the problem will be solved at that point in time or not, but that's one example. Yeah. Yes?
Do you have any anecdotal experience of using these kind of methods on multi-class problems in large data sets?
No, if I'm honest. In principle, so I just mentioned here that it works for the multinomial version of the logistic regression problem. So you don't even have to do the traditional one versus other decomposition of the problem. It just worked with the multinomial formulation of it. So it should be no different from what we demo tonight. Yeah. Yeah.
What are the advantages for using both L1 and L2 penalties instead of just using L1?
And so again, the point is that you don't know in advance which one you should use. I had a slide where, let's see, where I tried to compare the properties of both of them. Yeah. Oops, too much. There you go. So that's L1, that's L2, and so here I try to illustrate when you should use one over the other. But the message is that you don't know which one you should use. So you want to make finding the right penalty part of the minimization problem. So the penalty function, it's doing two things, right? Depending on the penalty function that you choose, it's doing shrinkage and it's doing sparseness control. But which is the right degree of shrinkage and which is the right degree of sparsity control, it's totally problem dependent. So we are just making the exploration of that part of the minimization problem. Yeah. And so sorry, just to say that point. So we saw that it took 600, no, what was it? It took 10 minutes to do all the values of lambda for one particular value of alpha. So I just show you really half of the calculations that we need to do. If we, in addition to that, pick 5 values of alpha, like we were saying, alpha 0, 0.2, 0.4, 0.6, 0.8, so it's 5 times that. So it will be 50 minutes. But so in an hour, you've done all this exploration of all the reasonable combinations of alpha and lambda. So you don't have to a priori say this penalty is better or this penalty is better, because the truth is that it depends on the problem.
Rather than doing a grid search, does it make sense to do a binary search? Like instead of between 0 and 1, go to 0.2468, do like 0.5, and then do the smaller half or the bigger half, and keep splitting it? Or is it some nonlinear function that doesn't make sense?
No, I think you may be into something, because remember, alpha is controlling sparseness. Right. So you go to 0.8 and you say, oh no, that's too much. Right. So the better solution is not going to be on the other side. Now you have to back up. Right. And so maybe, yeah.
So is there any downside of using both of them? Why shouldn't everybody use it?
Because you don't want to wait 60 minutes. And by the way, for a given alpha and for a given lambda, that's a totally independent computation. So you could have launched each job in a different processor. And so instead of 60 minutes, it's a fraction. But I think the only reason not, like, if the problem that you're trying to solve has, my intuition is that if the problem that you're trying to solve has like scientific consequences, like which are the genes that have an impact on this kind of cancer, you got to do this, right? And so,
I mean, in an hour to search 1 million variables isn't bad.
Exactly.
Besides, this is a job for me.
So clearly, for a given value of alpha and a given value of lambda, it's a totally independent task. We could either try to go one step farther, bunch of dot products. Can we? I don't think anybody has looked at that yet, at least not that I know of. So again, let's see if I can jump to that slide. right? Here's the essence of the algorithm, right? And if these are 1 million, well, in this case, sorry, the vectors themselves are not too long. I only had like 10,000 documents, right? But these dot products are totally independent from each other as well. And so I suspect that something could be done here as well. Anything else? Yeah.
Another question is, so do you see actually the accuracy improvements over ordinary regression?
Usually. I mean, that's what got Breiman on this path 15 years ago, that there's a lot of variability in the ordinary linear regression coefficients, yes. Yeah. Okay. Thank you, guys.